Um, it is now recording. So, uh, very warm welcome everybody to the Meet the Winners webinar for our Eyes on the Ground challenges. These were two challenges that we ran in collaboration with IFPRI, with ACRE Africa, with CGIAR, KALRO, and Lacuna Fund. I will tell you a little bit more about the individual challenges shortly, but for now, we're going to start off by hearing from some of our partners. So I'd like to first off invite Mr. Jawoo to introduce himself and to tell us a little bit more about IFPRI and the sponsorship of this particular challenge. Over to you, Jawoo.
Okay, sure. Yeah, thanks, Paul. Yeah, hello everyone. Thanks for joining us today. My name is Jawoo. I'm a research fellow, senior research fellow, sorry, working at the International Food Policy Research Institute, called IFPRI, and I'm based in Washington, D.C. IFPRI is a part of global network of 15 agricultural research institutes called CGIAR. I'm currently leading a CGIAR initiative called Digital Innovation, which sponsored this program. Today, I'd like to introduce you to the CGIAR organization just briefly. CGIAR is a global partnership that unites organizations engaged in research for a food-secured future, with the mission of transforming food, land, and water systems in a climate crisis. CGIAR was established in 1971, and it has been at the forefront of agricultural research, aiming to reduce rural poverty and increase food security, improve human health and nutrition, and also ensure sustainable management of natural resources. Today, CGIAR is the largest global agricultural research network with 15 research centers around the world and more than 8,000 scientists working on various aspects of agricultural issues around the world. In recent years, CGIAR has been actively using digital technologies and data science approaches to analyze a large number of research data from diverse sources to generate insight and support policy making. We leverage, for example, satellite remote sensing data or citizen science data and different machine learning techniques to monitor crop health, predict climate impact, and enhance yield predictions, etc. But even with those thousands of scientists using all these state-of-the-art tools, there are difficult problems that we have not been able to solve in agriculture. And the topic of this today's Zindi challenge we are going to introduce was one of them. I'm so grateful for Zindi and ACRE Africa to partner with us to organize this challenge and develop a promising solution through the collective power of data science community in Zindi. I'm very excited to learn more about how the winners of this challenge were able to develop the solutions, and very much looking forward to using the innovation in the field in the near future. So thanks for having me today, and over to you, Paul.
Thanks so much, Jawoo. Before I let you go, I wanted to say a special thank you. IFPRI and CGIAR have been long-term partners and supporters and collaborators with Zindi. So a special shout out to you and your teams for always being so supportive and always setting such great challenges for our users. Thank you so much. Okay. So next up we have Diana Machogu. Diana is a business development manager for ACRE Africa. ACRE Africa are the partners in this challenge and will be the ones putting these models into use after the challenges are wrapped up. So Diana, I'd like to ask you to tell us a little bit about ACRE Africa and about this challenge. Over to you.
Thank you so much, Paul. Yeah, as you have already introduced me, I am Diana Machogu, Business Development Officer at ACRE Africa. So a little bit about ACRE Africa is ACRE Africa is a brand name for Agriculture Climate Risk Enterprise. It was initially from the year 2005 to 2009, it was a project that evolved into now a fully fledged company. And this project was called Kilimo Salama, and it was funded by Syngenta Foundation and the Global Index Insurance, GIIF. After 2009, the company was registered as an insurance surveyor in Kenya, and we are a for-profit company, a social enterprise. So our core mandate is to, we design risk management solutions where we link stakeholders to solutions of insurance and climate change adaptation strategies to reduce agriculture and climate risks. We are also a licensed insurance intermediary, whereby we support local insurers to offer smallholder focused insurance across all value chains in different countries. Currently, we have offices in Kenya. This is where our main office is based at. We have an office in Rwanda, in Tanzania, and we have another office in Nigeria and Zambia. Then we have projects in different other countries in Africa, such as Uganda, Ghana, Malawi, and also Senegal. We offer various products, or we design different products for, that offer solutions to ACRE Africa, to agriculture insurance, to smallholder farmers, and such include, we have hybrid insurance, where it is crop hybrid insurance, where we have index and parametric and yield insurance. We also have indemnity insurance covers, such as livestock mortality, catastrophic livestock mortality, and loss of income. And we have different advisory products, such as risk profiling and assessment, risk management trainings, climate change adaptation and mitigation strategies, microinsurance product design. As I mentioned earlier, this is one of our key areas, and also we conduct feasibility studies. So we basically link farmers to insurers and different stakeholders, and also reinsurance companies. So to speak a little bit about this project, one of the innovations that ACRE Africa has is the PBI project, and this PBI is picture-based insurance. It was an innovation that helps farmers to relay information throughout the season to insurance to us, so that we can be able to offer various advisory products for them, so that we can be able to also, it is also a monitoring tool where we can be able to monitor the season through the farmer throughout the season. So yeah, this Zindi challenge, can't wait to hear how the winners of this Zindi challenge managed to offer this solution to ACRE Africa. Thank you.
Thank you so much, Diana. And yeah, I'm equally excited to hear more about the solutions, and even down the line see ACRE Africa putting them into this. I really appreciate your partnership, and appreciate you being on the call tonight. So now on to the main reason. Thank you to our partners. Now on to the main reason for our webinar today. Let me share my screen once again. Get this right. Okay. I'd like to introduce you very briefly to the challenges themselves, and then I will hand over to a winner from each of those challenges to speak a little bit in depth about their solutions. So, as you've heard from both Jawoo and Diana, the Eyes on the Ground project was a collaboration between ACRE Africa, KALRO, IFPRI, the Lacuna Fund, as well as the CGIAR CGIAR, to create a machine learning data set that provides a closer view of smallholder farmers' fields with the aim of developing this picture-based insurance framework. Zindi's part in that was to host two different challenges within this Ice on the Ground project. The first challenge was focusing on identifying crop damage, whereas the second challenge was focusing on classifying different types of damage within images. And most of these images are cell phone photos of crops uploaded by farmers. So in our first challenge, our winners were Mohamed Abdelrazik, who is on the call today, and you'll be hearing from him first. He's from Egypt. Ishtish Kumar from India, Katan Sa from Japan. We had more than 850 data scientists enroll in this project. We had nearly 5,000 submissions over the course of a few months, and the winning score was 6.67 root mean squared, which I'm sure we'll hear more about. That really means shortly. Second challenge was the crop damage classification challenge. As mentioned, this challenge was focusing on classifying specific types of damage within crops. This can be drought damage, pest damage, disease damage, and so on. The winners of this challenge were Hugh Pham Tran Min from China, Damola Oriola, who's on the call with us today, and Marine from Japan, and then Prang La from Vietnam. In this challenge, we had an amazing 1,044 data scientists enrolled. That makes it one of our most popular competitions ever on Zindi. Nearly 6,000 submissions and a log loss score of 0.47, which corresponds to 82% accuracy of the models. So I'd like to now hand over to first to Mohamed Abdelrazik. Just one second. Mohamed currently works as a data scientist in Abu Dhabi, although he's originally from Egypt, and he's been on Zindi for around a year. Oops, I'm sharing the wrong screen. I'm sorry about that. He's been on Zindi for around a year, and this is by far his best performance in a Zindi challenge so far. So definitely an up-and-coming data scientist to watch on the platform. And with that, I'll hand over to you, Mohamed.
Thank you, Paul. Thank you. First of all, thank you, Zindi, for this competition, for this amazing community. I learn a lot from people from Zindi, their solutions, their discussion. And in the first competition, what happened by removing the damage column and then rerun all models again, it was exciting, very, very exciting competition. First of all, I am Mohamed Abdelrazik, currently working as a senior data scientist with the Department of Culture and Tourism in Abu Dhabi government. Previously, I was working for one of the biggest pharmacy chains in Saudi Arabia as a data scientist. My main work for optimization and currently working for forecasting, sentiment analysis. But the main passion for me is computer vision. I really like computer vision competitions. I joined Zindi 3 years ago, but this is the first competition I won on Zindi. And alhamdulillah for for this competition. I will walk through my solution. Can I share my screen?
Yes, I think you should be able to. Please try. If you can't, we'll change the settings.
Okay. So I cannot prepare a PPT, but I will share my code and go through my methodology to win this solution. And to be honest, it was very basic strategy. After dropping the damage column, which caused the data leakage, based on Zindi coordinators rules, I trying to figure out which column I can use to infer a lot of information about the target, which is the extent I do a lot of data analysis and exploratory data analysis to figure out what is the distribution between the extent level for the damage and the growth stage, because I drop the damage column, and figure out that the S growth stage, I think it's referred to the small, or I didn't remember what it referred to, but I figure out that 95% of growth stage S has a damage or extent damage by 0. So I decide to drop all data which come from the growth stage S, because this, if it will go to the model, it will get the data highly drifted to 0 prediction, which will result in high root mean square error. So the first trick in this competition, first of all, I drop the damage column. After that, I drop all the data which come from the growth stage S. And this has a two advantage. It reduces the training data set, because we have a limitation. Our model cannot exceed 8 hours of training and 1 hour of inference. So this will save a lot of time for training. After that, it will avoid model drift. Then I will do the 5-fold using stratified k-fold solutions, stratified k-fold cross-validation methodology. After that, I prepare my training CSV file, reading the data set itself. Of course, I tweak the learning rate, the batch size to, especially the batch size, because it has to be fit on 16 GB RAM GPU. I use a lot of normalization values. I use the standard and the mean of ImageNet, but I got a bad result. So I tried to go with the 0.5 mean and standard deviation. This trick helped me a lot to enhance the score from 7.2 to 6.6. I use augmentation to avoid overfitting. So I use horizontal flip, vertical flip, and normalization. I use a simple model, which is EfficientNet P3 model, to avoid the long running time for the model to follow the rules, which is specified by the Zindi. The training time is limited to 8 hours, just 8 hours. Of course, my loss function will be the mean square error, because this competition is a computer vision regression model, not a classification model. So we have to change the last layer and the activation function for the last layer. And I run the model just for 5-fold, for the 5-fold, each fold 5 epoch, to avoid the maximum running time to be around 7.3 hour, 7.5 hours to follow the Zindi restriction. And that's it for the training. I use the model from the training script in the inference script. Can I? I use the model, my model from the training script in the inference script here. Same data augmentation, same everything. Just the model. I load I use, and after tweaking the data, I decide to go with the fold 4, 2, and 3, and 4, which from which I got the lowest root mean square error loss. So I drop fold 0 and 1. I just go with 2 and 3 and 4, equal weight. And after that, after the prediction, I figure out there are a lot of bad images, which has a zero extent damage, but in the data set, it's similar to a high damage level. So for this image, I decide to go by replacing every target if it's less than zero to be zero, because our range from 0 to 100. So anything negative from the model prediction, it will be zero. After that, I use post-processing based on the growth stage in the test data, based on the EDA I did for the training. 95% of stage S is zero. So I decide to go with any image in the test data has a growth stage S, it will be zero. And if it is, and from season LR 2020 or SR 2020, I use the target average. That's it. So my solution based on two main tricks. First thing, dropping the growth stage S from the training. After that, post-processing for bad images and post-processing for the growth stage S to force it to be zero. Because based on my experiment, there are high correlation between the cross-validation result and the public leaderboard result. So I suppose that the distribution for the extent damage across the growth stage in training is similar to the distribution for growth stage and damage in the test data. And simply, this is my solution for this competition.
Thank you so much, Mohamed. Appreciate your contribution. I'd like to give our attendees a chance to ask any questions. Please feel free to ask the question in the chat, or you can come off of mute and just ask the question directly. I'll give a moment for questions, and then we can move on to the next presentation. Okay. I don't see too many questions. I'll ask you one question, Mohammed, since we have some time. Oh, there we go. I see a question. Which algorithm did you use? Sorry if I meant it. Koduo. Mohammed, are you there? You're unmuted if you're answering.
sorry, I muted it by I use the efficient net model, which is a computer vision algorithm used for image classification. I tweak the last layer from the model. Instead of the classification, I make it for regression, because our problem is computer vision image regression, not image classification. The second challenge for CGIAR is image classification.
Yeah. I wanted to ask something maybe not so technical, but do you find that a challenge like this is relevant to your career and your work? Or is this are you doing this for fun?
For me, in my day-to-day job, I focus only on forecasting and tabular data, but my passion is in computer vision algorithm. I really like computer vision field more than NLP. However, NLP is trending and booming now, LLMs and ChatGPT. But I am eager to any computer vision competition on Zindi or other platforms. And I prepare myself for the next competition, which will start in 13 hours, which is for I think Malawi houses damage in Africa. So I will be there.
Excellent. We'll see you on the leaderboard. Thanks so much, Mohammed. I appreciate your time.
Thank you, Paul. Thank you for this opportunity to express my work and for this opportunity to find my passion in computer vision. Thank you.
Fantastic. Thank you. Okay, so that was Mohamed Abdelrazik. We will now move on to the one of the winners of edition 2, which was the damage classification challenge. I'm very happy to introduce Damola Oriola, who is a long-standing Zindian. Damola has been on Zindi um, for I think maybe 4 years or maybe even more than 4 years. Sorry, I'm having just some difficulty with the slides here, but give me a second. Um, this should, here we go, that should be right. Damola is better known as Flamethrower on the Zindi platform. He's really participated in many challenges. Finn is in the medals, I think 13 gold medals to his name. He's currently a data scientist with Invenium, which is a computer vision company based in France. So Damola, over to you.
Okay, hello everyone. Thank you, Paul, for the introduction. So just as Paul said, I'm Damola Oriola from Nigeria. I used to work as a petroleum engineer at Baker Hughes. Mostly my work involved working with data acquisition services in the energy industry. I'm also an experienced data scientist with some significant experience building some winning solutions for diverse problems in competitions organized by Google DeepMind, NASA, Fossil Group, Wadani AI. So my experience in data science is in both structured and unstructured data, but my current work as a data scientist at Invenia mostly involves working on computer vision solutions. So I'll just share my screen now so I could show this. Okay. So my team for this challenge was myself from Nigeria and my teammate Pham Vuhong from Japan. So we participated in the CGIAR crop classification challenge and we developed the second place winning solution. So I'll just be presenting our solution. So I'll just start with the challenge statement for those that might not really be fully aware. This challenge required building a machine learning model for identifying types of damages, crop damages in cell phone images of crops. So there were 26,000 images and 5 damage types, drought, good growth, nutrient deficient, weed, other, right? So a model was required to be able to be trained on the images with the different damages and end up predicting the correct damage for a particular crop image. So for this competition, the evaluation metric is log loss. So basically, log loss is all about the probability confidence that matches the targets, right? So this is an error metric, so lower the better. So there was one requirement for this challenge, which is the compute restriction. So for this challenge, the solution was required to run in less than 9 hours total time for training and inference on a single 16 gig NVIDIA GPU. So for this challenge, we trained it on an NVIDIA T4. So I'll just introduction for the data overview. So this is just a visualization of the images, just showing the different types of damage for different images. So when we look at the images, we see that there are different brightness levels, grainness levels of the crops. So one thing that we wanted to be careful about was not altering the images with augmentations that make it look unnatural. So this was one point that we took into account. So when we look at the distribution of the crop damage, we see that it's an imbalanced distribution. So the majority class, we have a majority class, which is WD and G, and then we have a minority class, which is ND and other. So ND and other, which is the minority class, is almost 10 times less than the majority class. So this is very important when training a machine learning model, because machine learning models are more prone to tune themselves on the majority class and not do as well on the minority class. So this was one thing that we took into account. So the next right now. Okay, so for the processing, just like I mentioned, we went with very light augmentation. So we just used horizontal, vertical flip transforms just to improve the diversity of the data for it to have good generalization with different orientation of the images, rotation transforms, zoom transform. But then we use brightness when we tested during validation. Heavy augmentations tend to give low scores compared to when we use like light augmentation. So after doing the different augmentation, we use a resize. So for this, we just use the fast AI default transforms, because when we try to use other augmentations, augmentation, it didn't give better results. So for data preparation, one thing that we need to do is ensure that we can somehow improve on the minority class or take the minority class into account. So what we did was we undersampled, we have one subset of the data where we undersampled the majority class G and WD. If you look at these two plots, the one below, you see the full data before undersample, you see the imbalance, right? So when we undersampled G and WD to be about 3,000 counts, so it can be closer to the DR distribution. If we try to undersample it too much to be completely balanced with ND and other, the model just ends up being worse, which you will see when we show the result. So yeah, we undersampled G and WD to 3,000 samples. So this ended up improving the generalization on the minority class without hurting the performance on the majority class, because of the type of metric that we are dealing with, log loss. If log loss is just looking at the confidence for all the samples, it's not really taking imbalance into account so much. So if you end up tuning the model too much to the minority class, you would have worse scores on the log loss. So this is something that we observed. So we ended up having another model just trained on undersample class to act as a regularization. So I'll just move to the model building. So we trained a classification model using after stratifying the data using k-fold validation on the crop damage. So to have a representative validation, ensuring that we have a good number of crop damage in both train and validation. So after we optimized our hyperparameters, trained after we optimize our hyperparameters on the validation set, see a good performance, which tells us the number of epochs and everything, right? We end up training on the full data when we now want to end up accounting for more data, learning from more data. Because of the compute restriction, we can't train 5 folds. We can't train 5 folds 5 times. So we just train on the full data. So very important for the training configuration is using one cycle learning rate, differential learning rate, and we also had custom heads. One cycle learning rate helps to have faster convergence. And then these are with the custom heads, we're able to optimize the model specifically on the crop damage task. So we tested several models from the team model, pre-trained ImageNet models, and we found these specific models to be perform best while taking into account the compute restriction. So we had EVA-based 448 trained on full data, epoch 6, and then we had a custom head that we used for it. So once we get the output from the EVA-based backbone model, we connect it to a custom head, and then we now make prediction for the crop damage. So when we trained the EVA-based, the next thing that we did a kind of a model distillation, because the output from the backbone of the IVA base is 768, and the output from the VIT base of 384 is also 768. So the moment we had tuned this custom head, instead of when we wanted to train the VIT base 384, instead of now reinitializing the weights all over again, we just take this custom head, which is already has some length weights for the task, and then we train the VIT base, train a VIT large 224, and we can't use the same custom head because the backbone has a different output, 1024. So we also train with a custom head for the VIT large 224. And then, just as I mentioned, we train just a single model on undersampled data. So we train a Convex small on the undersampled data, which is this flow, and then we use a custom head. So we use these 4 models, having trained them with the optimum configuration. So this is the model evaluation. So one thing that we did is, instead of just looking at the log loss, we looked at the log loss, we looked at the weighted log loss, then we looked at the log per class log loss for each class. So what we would observe is, for different models have different performances across the different classes. IVA base has one of the best log loss as a single model. For weighted log loss, just as we expect, Convex small 448 has the best weighted log loss. Weighted log loss means we are taking the weights into account. So the reason why Convex small has a better on the minority class, ND and other, as you can see, for, I think I can annotate, right? Yeah, okay, yeah. So as you can see, for the Convex small, it has the best performance on the minority class, ND and other. So different models have different performances, but if we had only trained a model with weighting into account, trying to take the imbalance into account aggressively, the log loss is worse, because now the tuning on the minority class is good, but the tuning on the majority class has dropped. So that's why for the Convex small, you see that it has the worst performance on the majority class and the worst performance for G and WD on the majority class. So after training these different models, what we did was we then assembled the 4 of them, including the Convex small. So when we assembled the 4 of them, you can see that the log loss for the 4 of them is 0.529, and the weighted log loss is still good enough. So at the end of the day, combining the undersampled model with the 3 models that are trained on the full data improved both the log loss and the weighted log loss. So this was important because there are several strategies you can take to optimize imbalance, but if you do it too much and you end up hurting performance on the majority class, then the model log loss score will be worse, which is why, for instance, Convex small is like this. So one thing that was very critical for us was, how can we improve on the minority class without hurting performance on the majority class? So if you see this table, you'll see that the performance for the tree, when we combine the tree model, is still good enough on the majority class, is still good enough on G, is still good enough on WD, and is better on ND and other. So this was very critical for us. If we used only IVA, VIT, and VITL without using this undersampled model, you can see that our weighted log loss is not as good as when we combine it with the Convex small. So the combination of optimizing our model to do well on the majority class and also improving on the minority class by assembling with an undersampled model was critical for us to achieve the second place, private 0.515 and public 0.532. So that's how we solve this task. Thank you very much.
Thank you so much, Damola. Let me just see if there are some questions. A question about the meeting record being shared. Yes, of course, this will be up on our YouTube channel in the next week or so. Okay, so then a question from Ronnie Leon. Why use 2 learning rate schedulers, 1 cycle LR and differential LR? I agree that these learning rate schedulers will make the model converge faster. Did you have anything to add for that question?
Okay. So one cycle learning rate is the scheduler, while the differential learning rates. Now, when ImageNet models are trained, right, they end up learning things like edge detection. So most times the intermediate and the later layers are more layers that should be tuned on the task itself, while you don't want to end up tuning the early layers too much. So for the differential learning rate, what happens is you use a lower learning rate for the early layers so that you don't lose that detection capability that it has learned from a vast amount of data, which are general detection capabilities like edge detection. But at the same time, you want it to tune very well on the task itself, which is the crop damage. So that's why the combination was necessary. By doing these two things, you are able to have faster convergence. If you just use the Fast AI library, this is actually what they have developed, and it works for most tasks that you would have to deal with, right? So it's from research. The research community has come up with this two combination of differential learning rate combined with the one cycle scheduler. So that's one of the things that was important for fast convergence. And the reason why fast convergence is important here is because if you train these models for too long, then you're going to have end up having longer training time. But because of the restriction, we need to do it in a very short time. And I'm seeing the question. Yeah, fast AI is good for most computer vision tasks, at least to give you a good performance. But if you want to have like the best performance on any task, you would need to explore you might need to integrate other ideas that might not necessarily be in fast AI, and you might need to experiment more and try things that fast AI might not have. So fast AI pipeline is good enough for you to have a good performance, but you might need to still check some of what's like the current state of the art research that you can still combine to improve. Yeah.
Great. Thanks so much, Damola. I was wondering I mean, before I ask my question, let me say again, if there are any other questions, please do speak it up now or type your question in the chat. Keep those questions coming. But my question is, I guess, because you work in computer vision modeling professionally, do you see major differences in this kind of work that you're doing on a competition versus the work you're doing for your job?
I would say most of my knowledge and experience actually came from working on computer vision competitions. So it's the same methodology. The only thing is because now we are thinking about deployment, right, for users, we might not be able to, for instance, assemble as many models. We might not be able to use all of this ensemble, for instance, improve the model from a log loss of like 0.54 to 0.51, but you need to consider the computational cost of doing that. So in production, in competition, you're trying to squeeze as much performance as you can get, but in production, really doing all of the different techniques that you would end up squeezing a little more performance, you might not need to do it in production because it could cost you more.
Yeah. Okay. That's really interesting. Thanks for sharing. So two more questions here. The first one from Ronnie again with the ensemble of four models, how long was inference? Did each image pass through all four models?
Yes, so inference was, and that's the thing, inference was 15 minutes, even using test time augmentation. So for each image, we would run this image, have an augmentation, 7 augmentations of this image, and then we'll pass it through the model, we'll get a prediction, get the mean of this prediction. We'll do that for all the models, and then we will now do a weighted average of the prediction. So even with the models that we use, and we were still able to run at 15 minutes for inference. Then the second question, yes, so we combined the different models to get a prediction for the crop damage itself. So basically, we predicted for the crop damage. That's what we just did.
Mohammed, you had something to add?
Yes, Paul, please. I agree with Oriola for his suggestion. What is the difference between competitions and the real life and production models? So I suggest in the upcoming competitions, can we keep the constraint for the computational power and computational time to make our models can be used in the production environment, and instead of just beating the competition, seeking for the best fifth or seventh digit after the decimal, to just ranking in the competition using a lot of computational power. So instead of this model be used in the competition itself only, it can be used in the production environment also. Because in the production, we have a trade-off between the performance and the prediction time and computational power. That's it.
Thanks. It's a great suggestion. I think this is what we are aiming for when we do these put these constraints on modeling on Zindi. Zindi's really focused on trying to produce real solutions that are going to be useful for ACRE Africa or for whoever the partner is. And actually, we're busy. You can watch the space, but we're busy working on a ML Ops focused challenge, which will in fact evaluate models and their performance beyond just accuracy. So looking at inference time, looking at a few other metrics in terms of performance on edge cases or those sorts of things. So we're always working on ways, and if you have other suggestions, you can pop me an email, and we'll keep trying to get better at it, because I think it's a really important aspect of what we're doing.
Okay, thank you.
Great. Okay. Are there any other questions or any other comments to add? I'll give a few minutes here, but I think we are coming to the end of our event. Yeah, I don't see any more questions. So Damola, thank you so much for that presentation. You really went into a lot of detail, and to me, very interesting to see the contrast between the two winning solutions, a very simple and direct solution from Mohammed, and quite a complex and carefully thought out approach from you, Damola. So really fantastic to hear your solutions, both of you. And as we're getting to the end of this webinar, all that's left is for me to say a very sincere thank you to all of our partners, of course, to our winners for sharing their expertise, and to all of you attending and paying attention and coming to learn or grow. I really appreciate your time this evening. I hope you learned something. I hope you enjoyed your time. And as I said, we will make this recording available, and we will see you hopefully for the next challenge. As Mohammed mentioned, we have a great computer vision challenge coming out tomorrow around helping to identify vulnerable communities in Malawi, communities vulnerable to landslides and cyclones. So we hope that you'll all show up and try to apply some of the things that you learned here today. With that, I'll say good night and have a very good evening.